Every text message, photograph, and high-definition video you have seen breaks down into the exact same microscopic building blocks. We call them bytes. This diagram shows how that unit works in practice. 1 byte equals exactly 8 bits, which gives a computer exactly enough space to store a single typographical character. So typing a simple word like hello takes up exactly 5 bytes of storage. Stack 1024 of those bytes together, and you get a kilobyte. In physical terms, that gives you enough space to write about half a page of standard type text. In the early days of computing, physical hardware placed strict limits on what a machine could do. Programmers had to engineer entire games and business applications to fit onto a standard floppy disk, capped at a limit of 360 kilobytes. By successfully squeezing working software into a few hundred kilobytes, early engineers proved that complex human ideas could be miniaturized into a digital space. As those ideas grew, the hardware expanded to handle them. A megabyte is roughly 1 million bytes. In the 1990s, owning a massive beige desktop tower equipped with 500 megabytes of storage was the gold standard for home computing. That extra space allowed computers to process multimedia. We moved past plain text, saving 1 megabyte digital photos and 5 megabyte MP3 files. Then came the gigabyte, roughly a billion bytes. This mathematical leap allowed people to carry massive media libraries with them anywhere. Devices that held a gigabyte or more meant you could easily drop hundreds of photos or an entire music library right into your pocket. Today, the gigabyte dictates the capacity of our personal hardware. Most smartphones start with a baseline of 64 or 128 gigabytes to handle modern apps, high-resolution cameras, and demanding operating systems. If you converted a single gigabyte into plain text, it would roughly equal about 1,000 thick novels. The gigabyte marks the upper boundary of human-scale data, the maximum amount of information a single person can intuitively understand and actively carry around. Once you move past 1024 gigabytes, you cross into the realm of the terabyte. At this volume, data shifts off your phone and onto external backup drives and standard cloud storage infrastructure. To picture the physical scale of a terabyte, look at the Library of Congress. You can take the text of that entire sprawling physical archive and fit it onto a single 10 terabyte hard drive that sits neatly on your desk. Multiply that terabyte by 1,000, and you reach the petabyte, a quadrillion bytes. We don't interact with petabytes in our daily lives, but they are the standard working metric for major technology corporations. Managing a petabyte requires heavy-duty industrial equipment. Companies like Netflix use petabytes to host their global video libraries, and research facilities like CERN use massive supercolliders to generate and store vast oceans of particle physics data. At the petabyte level, we are no longer discussing information meant for a single human being. We are dealing with data that requires global networks and supercomputers just to process. The next tier up is the exabyte, 1024 exabytes. This is the unit where data volume stops tracking individual companies and starts tracking human history. This chart tracks our historical data output. Back in 2001, the total size of the entire internet equaled about 5 exabytes. Today, that exponential tower of blocks shows humanity generating those same 5 exabytes every single month. Because of that acceleration, governments and major cloud services now measure worldwide digital output in zettabytes. 1 zettabyte equals 1024 exabytes. As the chart morphs into a global map, look at real-time internet traffic. In the year 2020 alone, global traffic hit roughly 4 zettabytes. That single year of digital movement equals about 120 billion 4K movies streaming across the planet. At this magnitude, data acts as a planetary phenomenon. It is a metric that tracks the sum total of global digital movement, scaling beyond the control of any single entity. That brings us to the largest official unit of digital storage, the yottabyte. That is 1024 zettabytes, or 1 septillion bytes. You cannot build a yottabyte hard drive. The yottabyte is currently theoretical, as no physical system on Earth can store one. If you could build a system large enough, a single yottabyte would house every document, song, photograph, and video ever created in human history, and it would still have plenty of empty space left over. Engineers and scientists don't use this unit to measure current reality. They use it to mathematically prepare for the compounding growth of our future data output. The concept of the yottabyte serves as a warning. It is a mathematical indicator showing how fast our digital footprint is outpacing our physical hardware. 30 years ago, a 500 megabyte hard drive felt like a massive achievement. Today, that amount of space is a rounding error compared to the invisible oceans of information we generate every time we pick up our phones. But no matter how vast that planetary scale becomes, the underlying architecture never changes. Every petabyte of scientific data and every zettabyte of global internet traffic still breaks down into stacks of individual microscopic bytes. These prefixes track the increasing complexity of our global output. Each new unit marks the exact point where our collective digital footprint outgrew the desktop, outpaced the library, and began to rival the scale of the planet itself.